this is the last type of question stuff we're going to be doing with the distance time graph stuff. Next week, I've put up a schedule of revision things that I want to do. The first one's going to be on fractions, decimals, percentages. I'm currently putting together the revision materials for you. Before the lesson, it's best if you've had a go at the questions rather than come to the lesson and expect me just to teach you how to do it. You need to have tried first. So each of the sheets need to be done the day before. And then you come to me with questions. It's not going to be me sitting making videos and teaching you how to do them. All the questions have mark schemes with them, but mark schemes can be confusing, so just bear that in mind. Okay, today's lesson, last one of the year, apart from a couple of projects. We're going to discuss different ways that time graphs can be used. This one is a fairly common type of question. You've got an exercise on it. It's trying to work out how deep is the water if a constant flow of water is coming in. So the water dripping in is always coming in at the same speed. Okay, it doesn't change with time. It comes in same amount of water, and you've got to think what happens to that water. And the easy way to think of it is about what would happen to a constant volume. Now, volume on this diagram could be represented by 1 square. So 1 square goes in, and it would smear out along the bottom of the graph of the thing to about 1/3 of the height of the square. So in one time we get about 1/3 of the square coming in. So let's go like that. Next square drops in, and again we'd get about 1/3 of the square. And because the walls are constant distance, we wind up with a constant speed of, or constant increase in the height. I'm just trying to get this to move up to a, so we can see the graphs we're doing. So for every second we're getting about 1/3 of a square coming in, and that leads to a constant increase in depth of water. The depth is where the water surface is, depending on how long we've been waiting, how many squares went in. So let's move to the second one, the cone. The first square goes in, and there's hardly anything there, so it goes in, and it will fill up quite a large amount of space. So 1 square goes quite a long way up. In fact, it'll probably be more than 1 square high, it'll be quite a lot higher. Another square goes in. Now it's spreading out a lot more, so it's not increasing quite as much. So the next level spreads out a little bit more, so we go up from here a little bit more, but less increase. There we go again. Next square comes out and it really smears out quite broadly, so it reduces again. And the further we go up, smaller and smaller lines can be created. So there's smaller and smaller increases as we go through. And the sort of graph you get for the cone would be a fill like this. As you get to the top here, for 1 square being dropped in, it would spread out to almost hardly any change. You wouldn't notice in that time. So this sort of graph, 1 square's gone in, it's gone in, spread out quite a lot, hardly anything at the start, and then so it's got to rise quite quickly. Rises quickly at the start. Next thing, section up, it's going to be rising at the same rate as this piece, but spreads out again, so it goes slower, 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 slower. So the last one I'm going to show you is this one. And again, think about your square dropping in, or your cube dropping in really. In a constant time, this volume drops in, starts out, and it spreads to the bottom. So again, we're getting quite a wide area at the bottom. Next bit goes in, it's a little bit wider now, this section. That means it won't climb quite as tall, because if you remember, volume is area times depth. Remember the volume of a prism. And each of these we can think of as little tiny prisms. So we've got tiny little prisms all the way up. And the area here has got wider, so the depth is smaller to keep the volume coming in the same. Okay. So all of these are actually volumes coming in. Okay, and that's volume of a prism. So we put quite a bit in. Next bit slows down. Next layer up slows down. Until we get to this point where there's a really thin layer going in. Hardly anything increasing. So about halfway up, we get virtually no increase. And then here, the area gets wider, but it's narrower, so the height must get more. Okay, so this is a big area on the bottom here, so it's got to rise up a bit quicker, so it starts picking up again. And so it goes over and up and then back up again. So you've got to think what happens to one unit volume. If it's got a small area to spread out, it's going to rise quickly. So that depth is going to go up quickly. If it's got a wide area, the volume, to keep the volume the same, the depth must increase slowly. In your worksheet, you've got a few questions like this. There's only 6 of them there because I'm expecting you to start preparing for your revision. There's those 6 questions. What do you think is going to happen? We've got something at the bottom here which looks like the funnel. Starts with virtually no width. So it's going to rise really quickly, gets out to something which is a bit like the tube at the start, a constant width. So it's going to rise at the same rate. So it's going to be a sloping line. And then it does a reverse, but a lot quicker. And do try to show that change in speed. I know these take a while to get your head into, but do think what happens. So this one, going up, it's like our tube to start with, and then suddenly the tube gets narrower. Does that mean that the volume is going to go higher, quicker, or slower? Small area at the bottom. This one starts quite wide. Is that going to lead to a large increase in the depth, or a small increase in the depth? Gets to a small area across the top, same volume going in. This one's a bit horrible. This one's pretty much the same as that, but do take into account the shape of the shoulders. And there's your last one, the flask. Okay,